Hello, our talk today will be about inverse functions. This presentation was put together by Samba Danfa, Diana Huang, Brendan Fahey, and Mengmeng. In our talk, we will first review one-to-one and onto functions, then we will define inverse, and then examine invertible functions, and finally discuss methods for finding the inverse of functions. First, in order to understand invertible functions, we have to review one-to-one. A function is one-to-one if a equals b whenever f of a equals f of b for all a and b in the domain of f. That is, for every element in the domain, it maps uniquely to one element in the codomain. The function from xyz to 1, 2, 3, 4 with f of x equals 1, f of y equals 3, and f of z equals 2 is one-to-one because every element of the domain maps uniquely to one element of the range. That means there are not two elements in the domain that map to the same element in the range. Another example, the function f of x equals x squared is not one-to-one because both f of 1 and f of minus 1 equals 1, but x equals 1 is not the same as x equals minus 1. To review onto, we define onto as a function from a to b that for every element of b that is in set B, there is an element little a in set A with f of a equals b. Another way to express this is for all y, there is some x such that f of x equals y, where the domain of the function is the domain for x and the codomain of the function is the domain for y. So, in the example from the previous slide, the function from xyz to 1, 2, 3, 4 with f of x equals 1, f of y equals 3 and f of z equals 2 is not onto because there is no element in the domain that maps to the element 4 in the codomain. One-to-one correspondence is a function that is both one-to-one and onto. In order for a function to be invertible, it must have one-to-one correspondence, and Samba will explain why this is.
Hello everyone, my name is Samba and I'm here to give you a definition of inverse functions. First, if there is a one-to-one correspondence, f from set A to set B, every element of B is the image of some element is A, and that is called an onto function. Also, if we have every element of set B being an image of a unique element of set A, we call that one-to-one function. So to have a one-to-one correspondence, we need to have both a onto function and also a one-to-one function. So if those conditions are met, the new function that's going to be created is going to be the reverse of those. And that's going to be defined as a function. But to put this in layman terms, we can call a function A to do something and then the inverse function to undo. So let's say we give a function A, which is the do function, we give it some initial value. We perform some operations and that gives us some output. The inverse function would take that output that we had in the answer, perform some other operation, and will arrive back at the original starting point. That is pretty much in a nutshell how to define inverse functions. Another thing is important is the notation. If we have a function fx and we want to find the inverse of it, as you can see, this is the only thing we have to do, which is the f negative 1, which is not to be confused by a power of negative 1 by any means. So, and the inverse of a function is not one-to-one correspondence, will not have the inverse function will not be considered a function. So I can give you a brief example. We can have a B and C mapping to 1, 2, 3. in this situation, if we get the inverse, we'll just have one mapping to A, and that will give us a function. But if we have A, B, and C, this will not qualify as a function, because if we invert it, we have one mapping to A and B, which is not defined as a function. So to give you a complete example, we added a slide that will exactly give you exactly what the real definition of this means. And it is exactly like this. As you can see, A mapped to, it is mapped to every element, and the same thing applies. And this is exactly the definition of an inverse function. All right. And to talk about the next slide, we have Brandon.
Hi, I'm Brendan, and I'm here to talk about invertible functions. Alright, so I'm here to show you some examples of invertible and non-invertible functions. So let's start with this first example from the book, chapter 2.3, problem 29. It says that show that f of x equals the absolute value of x from the set of real numbers to the set of non-negative real numbers is not invertible, but if the domain is restricted to the set of non-negative real numbers, then the resulting function is invertible. So let's start off by proving that the function is not invertible for all real numbers first. Let's consider f of 2 and f of negative 2. We find that the absolute value of x is both 2 and negative 2 for both of those values, because they would both equal 2. So that means that when this is inverted, when the function of y equals 2, it could correlate to either 2 or negative 2. Ergo, not invertible. However, on the domain from 0 to infinity, all values of x equal the corresponding x, thus this becomes an identity function, so it is in fact invertible. My second example for you is of one that is invertible. If we take the function f of x equals 3x plus 6, first of all we'd have to answer the question, is it invertible? And it would be, because it is a increasing function, and since it is increasing for all real numbers, that means it has to be invertible. So then let's find the inverse. Let's suppose that y is an image of x such that y equals 3x plus 6. And then you just solve for x, and we would get that x equals 1/3 y minus 2. And so the inverse function of y is equal to 1/3 y minus 2. And here to talk about finding the inverse is Diana.
Hi everyone, I'm Diana, and I'm here to talk about the methods to find inverse. So let's look at the first one, which is the most straightforward one. Use the definition. Here's an example. F maps the set of 1, 4, 7 to the set of 8, 19, and 40 such that f of 1 is equal to 8, f of 4 is equal to 19, and f of 7 is equal to 40. And this is obviously this is an invertible function, and let's see what's its inverse. So the definition of the inverse function tells us that if f of a is equal to b, then f inverse of b will be a. According to this, we are gonna get f inverse of 8 to 1, and f inverse of 19 is equal to 4, and f inverse of 40 is equal to 7. And now we go to the second method, which is invert the mapping. So let's see an example and illustrate what does that mean. So f is a function that reflects a point through the origin. What is its inverse then? So what this function does is basically take in the value of a and give you negative a back, which is flipping it through the origin. And then when we want to invert the function or invert the mapping, we just flip it back. And in that case, the inverse function will take in
-1 as a -a as an input value, and then give back a as an output. Now we have the third method, which is solve for x. So if f is a function that maps the set of integers to the set of integers such that f of x is equal to x plus 1, then we want to find its inverse. So in this case, suppose x is the input, or x is the input and y is the output. So now we want to reverse the function, so we want to put x as the output and y as the input. So what we want to do is just to solve x. Now x is equal to y minus 1, or in other words, it's just that we have a function that takes in y as an input and give back y minus 1 as the output. So here we have the inverse function of f of x, which is f inverse of y is equal to y minus 1. And that's pretty much about my methods. Thank you everybody for listening.